My name is Gary Liku, and today I'll be talking to you about chaos testing and how we used it to uncover some kernel scaling issues. So for a quick agenda, first we'll start off with an introduction about myself and my team and the systems we manage. Then we'll discuss the sporadic scaling problems we encountered. After, we'll talk about chaos testing as an investigative tool. Then we'll dig into the problem as threads, or maybe it isn't. And then we'll discuss profiling/proc for a little bit. And finally, we'll end with the mitigation efforts we came out from. So I'm part of the Bloomberg Trading Systems Runtime SRE team. We have over 300 managed machines, and these are all pretty big hosts, about 1 terabyte of RAM, 72 hardware threads. We mention this because it'll be relevant a bit later. Two of the biggest products that we support are AIM and TOMS. These are the buy-side and sell-side order management systems, respectively. And for those of you without a background in finance, roughly speaking, people on the buy side want to buy securities, and people on the sell side want to sell securities. And those are what those two products do. And all of our machines run a shared Bloomberg environment. So some of the attributes of that environment are a lot of shared memory, high volume of IPC, farms for high CPU jobs. And all of these aspects make it pretty suitable for vertical scaling, so we can take as much advantage of the shared memory as possible, less latency for IPC. We have lots of free CPU to use. And one other aspect of our machines is that we use precision time protocol on some of these for certain time-sensitive applications. PTP, for short, is a version of NTP, but you can think of it as having higher time resolution. And for this talk, we'll focus on a subset of high-end proc Linux hosts. So the story starts with some new clusters added to our data centers. We're slowly migrating workloads to take advantage of these new hosts, and everything looks good until we run into our sporadic scaling problems. So we see several seemingly unrelated issues become more common. And some of these are pretty generic. Hosts getting hung are very slow, happens all the time. Some services are slow to start up or shut down during our weekend load testing. One interesting thing that we found later on in the investigation is this was usually on scripts that were running PS or reading/proc. And PS and /proc are used for monitoring. And the problem that we see is that now they have a significant effect on our system. And this is particularly bad for a reason that one of our colleagues described in an article below. He coined the term the non-interference prime directive for visibility, and that states that the addition of any metrics acquisition subsystem should not noticeably affect the performance of the measured system. And that intuitively makes sense, because if your monitoring tools are changing your system, you're not getting accurate metrics on what the system itself is actually doing. You're being interfered by your own monitoring tools. And we had some more scaling issues. We had monitoring that were missing observations, and this was outside of those that were generated by PS. And most importantly, we had our PTP health check failing sporadically. And because this has real-time requirements, it's very sensitive to load, and it also needs 4 instances of clock drift within 1 minute to fail, so we knew these weren't just one-off issues at that point. OK, so when we see all these issues at SREs, what should we do? Well, we should ask what our metrics are telling us. And here we have a graph of one of our clusters by thread count. And this is a time series, so our x-axis is time, our y-axis is threads. And each colored line is one particular machine. And you can see all the way on the top right over there, we have our PTP alert come out on one particular host. And you can see it's a clear outlier with respect to threads. Most of our hosts are hovering around 200,000 to 250,000 threads, but this host in particular broke the 300,000 mark. So this gives us an idea that these alerts might be correlated to high resource usage. This is expected for heavy workloads, but it might be an indication of resource contention. But the problem is we're not really sure what resource that might be, so how can we further investigate this? And this is where we come up with chaos testing as an investigative tool. So the Principles of Chaos, a nice blog about the philosophy behind chaos engineering and chaos testing, states that chaos engineering is the discipline of experimenting on a system in order to build confidence in the system's capability to withstand turbulent conditions in production. So this is a good definition of chaos testing, but the problem is this isn't really what we're doing. We already know that our production systems can't withstand something. There's already a problem, but instead we want to turn this on its head, and we want to use this to investigate what the problem actually is. So we have some signs of a resource contention issue. We want to use chaos testing to replicate it repeatedly, and then once we have a repeatable chaos test, we can isolate the root cause and use it to investigate further. So how do we orchestrate our chaos tests? In Bloomberg, we have internal chaos testing tools called Chaos Commander and General Disarray. We use Chaos Commander for orchestration, and we use General Disarray as the executor for the tests on each host. And for this particular set of tests, we had one experiment per resource type, so we could isolate all other variables. And one other thing we wanted to add is a simulation of reading/proc. Because we saw this was associated with some of the slowness in our startup and shutdown scripts, we thought this might be valuable to have in the background. And for our nproc test, we're going to be using idle threads to make sure that any work that those processor threads might be doing won't actually affect the system itself. And what's nice about this is that we can use our already published metrics for monitoring the test itself in addition to monitoring our systems. And we can also create fail-safe monitors based on the metrics. So if we see that our test gets out of control, we can see that automatedly, and we can shut down the test just based on our metrics. So this is Chaos Commander. And even though this is an internal Bloomberg tool, I thought it'd be valuable to share this slide so you can see some of the properties you might want in your chaos testing framework. So this is the Lots of Threads game day. The title is at the top. And some of the attributes that we have on Chaos Commander are a big red button to stop running experiment at any time, which is really important when you're chaos testing. If things go wrong, you want to break glass and shut things down as fast as possible. On the left, we have a run or schedule button. And that doesn't actually immediately run the experiment. It just generates a ticket that needs approval to run the experiment, so we prevent any accidental hiccups by accidentally starting an experiment. And on the bottom, we see a set of operations. All of our experiments are composed of operations. And an operation is just one or more programs. And in this case, they're generally dedicated to a specific resource that we're testing. So now we run the experiment. And this is one example of our Lots of Threads experiment. And we can see just before the experiment starts, we have this nice graph of processes and threads. Our threads are in yellow. Our processes count is in green. And we see just before the experiment starts, our thread count is around 50,000. And just after, we hit 350,000. So the experiment is clearly running. And what's more is that you can actually see some of the symptoms that we've been observing on our systems, namely the missing metrics. They're clearly very spotty while the experiment is running, and they smooth out immediately after the experiment ends. And it's also pretty easy to see the experiment duration as our thread count returns to normal relatively quickly. Here's another experiment. This was not for threads. This was for CPU hog. So here, we just loaded our CPU. And the reason I brought this slide in is because we actually see some missing metrics on this test as well. And this is to say that all of our tests had some of the symptoms, but only one actually reproduced all of the issues altogether. And that's what gave us the data to know that we were confident that one particular test was responsible for our contention issues. So how do we know the experiment was successful? Well, like I mentioned, many of the issues that we were expecting emerged. We had the 4 missed PTP checks and our PTP alarm. We had our gaps in monitoring. We had our high system CPU with our tasks hanging. And not only that, but this was able to be reproduced on multiple hosts with the same resource test, and that is threads. And this is surprising, as we expect it to scale close to about 4 million, which is the PID max by default on Linux. And we only got to about 300,000 threads before we saw major issues. So we knew we were about an order of magnitude off from what we expected to be able to scale to. And what's really important here is that repeat experiments gave the same results. So this built a lot of confidence that we were on the right track. So for a quick summary of what we've gone over so far, we had several issues when we were scaling: PTP alerts, our slow start and stop scripts, particularly those calling PS or reading/proc. We had hanging and slowness throughout several tasks. And then we designed experiments to explore the potential causes. We had one test per resource. Then our test showed that nproc, or threads, were the culprit. As I explained below, because our process count is so much lower than our thread count, processes are in the tens of thousands, while threads are 50 to 100,000 to 200,000. We will be using threads as a shorthand. So when I say nproc, in your head, just think threads. And as we saw, the alerts trigger at significantly lower than our PID max value, and the repeat experiments show similar results. OK, so the problem seems to be threads, right? Well, not so fast. /proc is an atypical directory. It's created on demand. The Linux kernel keeps track of these processes and threads similarly in this directory. So you can see a sample program I run here called lots of threads, where I spawn 10 threads from a main program, and then I get the PID below. Once I dig into the /proc PID directory under tasks as well, I see a bunch of smaller directories with all the thread IDs of the threads that were spawned, and we can verify that with the ps command I called below. And one important thing to keep out for it is the TGID column. We'll see that come up later. OK, so we know that our problem is with /proc. We know that's related to threads. So what's really going on? If we're just reading a directory, it seems to suggest that there's a problem somewhere in the kernel. And when you dig into the kernel, you find this proc PID reader function that actually does the work of generating those process directories for you. And for the purposes of this talk, we'll be working with a 3.10 kernel. So if you're using Ubuntu 13 or Red Hat 7, you're most likely running the same kernel. And don't dig into this function too much. All I want you to take away from it is that it's used to generate the /proc process entries. And the main work of this function is done in this loop where we iterate over tjids. And we repeatedly call this next tjid function. Keep that in mind shortly. OK, so now we see that our problem is isolated to the kernel. We think that it might be involving this proc PID reader function. So let's do some profiling to see if that's really the case. So what we're going to do is we're going to rerun our chaos test, and we're going to profile at the same time. And we're going to use the /proc profile subsystem to do this. It keeps a counter of all the function calls of the kernel functions, and we've graphed that below. We also have the background thread count as the x-axis and the number of clock ticks as the y-axis. And after we do that, we see these 4 functions as by far the most called functions at the time. And we'll go through these one by one. So the top one that grew pretty tremendously, seems to be exponential behavior, was the native safe halt function. So this function is actually a no-op. It means your threads are not doing anything at all. And that's a big sign of a resource contention issue. Usually when a thread or process is waiting on a resource, you'll do nothing, or you might spin, something along those lines. So this is a lot more evidence that we're on the right track, that this is indeed a resource contention issue. Then we see the find PID NS function. We haven't encountered that before, but it seems a bit relevant. It's finding a PID. We're looking through /proc. Let's keep that in the back of our mind. Maybe it might be relevant later. We see one more come up, mutex spin on owner. For reasons we'll discuss shortly, this isn't as relevant to our problem, but it's something I wanted to include for the sake of understanding that your data might be telling you different things. And finally, we have our old familiar friend, the next tjid function. So this definitely tells us that we're on the right track and something is up with that proc PID reader function. All right, so a little bit more kernel stuff, and then we'll be done with it, I promise. Next tjid is called from our proc PID reader function, as we saw on the earlier slide. So let's dig into the next tjid function. And when we do that, we see some interesting stuff going on. We call an RC read lock, then we call a function called find GEPID, and after that, we call an RC read unlock. Now, this is great. Usually when you see some type of contention, locks are involved. So let's build some more confidence that, again, we're on the right track. All right, then we want to dig in a bit more. Let's see what that find GEPID function is doing. And when we do that, we actually see it's calling the find PID NS function that we saw earlier as one of the top most called functions when we were profiling. So this is great. It shows that a lot of the functions that we're spending a lot of our time in are all under the proc PID reader function. And one other thing I want you to take account of is that this find GEPID function and the find PID NS function both take a PID namespace as an argument. That will be a bit relevant later on as well. All right. So like I mentioned, the locks are a good candidate for the cause of contention. So our problem's done, right? We see contention, we see locks. We can just conclude right away that the RC locks cause contention. Problem solved? Not quite. So the issue with this is that RCU locks are actually designed specifically to avoid blocking on readers, but they allow blocking on writers. So the issue is that our data shows we have contention on readers. All we're doing is reading the /proctor or using PS. We're not seeing as many problems with forking, for example, which would be a writer. So what's going on here? Well, I'm not exactly a kernel engineer, but I am quite good at Googling. So with some internet hunting, I found the following quote from Paulie McKenney, who's actually the maintainer of the Linux kernel RCU implementation. And this code is about 20 years old, but it's surprisingly relevant to our problem today. And just to read it quickly, the problem is get PID list traverses the entire task list in order to build the PID list needed by ls/proc. It read-holds task list lock during this traversal and blocks updates to the task list, such as those performed by fork. On machines with large numbers of tasks, this can cause severe difficulties, particularly given multiple instances of certain performance monitoring tools. So this seems really relevant to us, even though it's about 20 years old. It talks about ls/proc, it talks about blocking, large number of tasks, and most importantly, it talks about how performance monitoring tools might be interfering with your system. And what's the problem with this? It's a violation. And when you violate the prime directive, you make Picard very upset. So now we can see from the quote that contention should be mainly in writers, but our data still suggests that it's actually found in the readers. So we might want a bit more data to actually support this conclusion, right? And let's see where the time is spent. We can look at our read-dir call. So read-dir returns a stream of entries, and we can see how much of our time is spent in the first loop compared to the rest of the loops. If our theory is correct, most of the time spent is in building the task list, so it should be predominantly in the first loop, and then the rest of the loop should be much smaller spent time. And while we're doing this, we also want to rerun our thread chaos test in the background to make sure we're recreating that contention that we've seen. OK, so we've done this experiment, and now we see the following data. So our blue line is the time spent in our first loop, and our orange line is the time spent in the rest of the loops. And there are around 200 loops in each read-dir call. So it's not just that there's only 2 iterations that you're making. There are plenty of iterations. And even in spite of that, the first loop takes up more than half of the time spent. So this is a lot of good data that tells us that we're on the right track. And again, just to summarize what we've done so far, chaos testing told us that our problems are correlated with high nproc and high read usage of /proc. We use the /proc profile subsystem to profile the kernel functions used while reading. We further isolated to the set of functions responsible for building the /proc PID directories. And we found that our data suggests contention is on readers, as most of the time is spent in the first loop, and it seems to be spent building the PID list, something that is exclusively done by readers. Again, the design of the RCU lock suggests contention on writers, so there's still a bit more investigation to be done, but for now, this is enough information for us to take action. So what can we do? Here's some mitigation efforts if you're also facing this problem. Because our issue are tied to high nproc, well, we can dig into that kernel-related function. And like we saw earlier in the find PID ns function, that actually takes a PID namespace as an argument. Because we saw our contention seem to be exponential, if we keep our PID namespaces small, that search time shouldn't be as cumbersome on our systems, and we can take advantage of that through containers. Docker, Kubernetes, they give you PID namespaces for free. So you might want to consider moving some of your workload to these containers. And because we see this as a kernel issue, it might be interesting to look at some kernel config functions. And in fact, there's actually a config RCU fanout variable that you can tweak. And the documentation for this says that lower fanout values reduce lock contention. Great, sounds like something we might want. But they also consume more memory and increase the overhead of grace period computations. So there might be some unintended consequences of tweaking with this, and this might not be a path that we would necessarily want to go down without some more investigation. But it is an option for you there. And one other thing to keep in mind is that RCU locks aren't just used for the proc PID data structure. They're used for other kernel data structures. So tweaking this one config will have far-reaching effects throughout your system, so you want to be very careful with this. What else can we do? Well, we can add nproc as a factor for load balancing. And again, because these things look exponential, reducing our nproc by half will give us 4x more load to work with. And to some extent, you do this naturally, as your load is naturally going to be correlated with higher nproc values. But in this case, we made it explicit that we were balancing on threads. Some other things we can do are monitoring and alerting on threads. And for this, we'd want to do this on a per task and a per host level. So per task helps us hunt down any big users of threads so that we can have them optimize their thread usage. And the host monitoring will let us know when we hit that 300,000 mark, and we might be in trouble of more issues on that host, so we can take some manual intervention to resolve that. So like I mentioned, we might want to find some users or find some applications that aren't using their threads optimally. And you might be thinking, wow, that sounds like a major pain to get people to redesign their entire applications to be more optimal for threads. But because threads were so cheap previously, we actually found there was a lot of low-hanging fruit. In particular, there were a lot of libraries, job queues, and even things like the JVM that had default thread pools that defaulted to the number of cores on your machine. And because we used really large machines, well, each instance was basically assuming that the machine was for itself and eating up all of our cores. So that's not efficient on our large hosts, and we went to these developers and we asked them to tweak their config a little bit and roll it out. And as we see, for example, the JVM has default thread pools for garbage collection and the JIT compiler, so you can reduce that with just a few config options on the next run of your Java application. And also, we made an effort to review some threading best practices. Because even idle threads have an impact here, we want to join on threads as soon as possible so they're not affecting our system any longer. And one other thing we can consider is that this is less of a problem in later kernel releases. We see from more profiling and chaos testing that this is closer to linear growth with respect to thread counts. And I believe there's a talk on implementing kernel upgrades in your system tomorrow, so stay tuned for that. All right, so in summary, what have we done today? We've observed several issues with scaling. We've designed experiments to explore several potential causes. The experiments pointed to one particular resource as the culprit. Repeat experiments gave us the same results. Kernel profiling confirmed that these were indeed scaling issues. Further investigation led to the specific functions in the kernel that were responsible for the scaling issues. And with that information, we were able to implement some mitigation techniques. So I'll leave you with this. Chaos testing is a great proactive tool. That's commonly how it's used. But in this case, it's actually pretty useful as an investigative tool. And what are some of the problems that you might want to use this technique on? Problems that are difficult to reproduce. If you need to orchestrate your system in a specific state, you might want to use chaos testing, as that helps you, that gives you a framework to meaningfully organize and do that in a repeatable fashion very easily. If you have a wide-ranging problem, that gives you more samples of data, and that lets you build confidence that your conclusions were correct. If you see a problem on one or two machines, chaos testing might not be the best tool for the job there, but it still may be useful, just something to consider. And also, one nice thing about this technique is that it gives you a bit of a regression test for free. If you see that your system has implemented your mitigation efforts, you can rerun your chaos test and see the outcome. If you still have the issue, the chaos test will show it for you. And if not, well, then you pass your regression test. All right. And with that, I just want to give some special thanks to the TS SRE runtime team and LMS team for all their help, as well as the Bloomberg Resilience Engineering team for the great tools they've created. And that's all.